sweet as usual. Thanks, and I'm realizing as I was preparing this talk, this will really be about anti-diffusion. I'll explain it.
Plus.
And I want to acknowledge my absolutely wonderful collaborators. It's been an absolute pleasure to work on this topic with Kasturi, Laura, Greg, and Colm. And this is all a product of the Geophysical Fluid Dynamics summer program at the Woods Hole Oceanographic. And if you haven't heard of it, please ask us. So here's the motivation, right? I want to study stratified turbulence, and I want to define it first. So stratified turbulence is basically three-dimensional chaotic flows, but where the vertical fluid motions are strongly inhibited by the local stratification. And as a result, the flow is very strongly anisotropic, with larger scales in the horizontal than in the vertical. And occasionally, it can even be intermittent. And this is a picture of the entropy in a strongly stratified turbulence simulation. And you can really see these long horizontal layers in entropy to which you have these localized patches of turbulence that you can see very well. And you can see that the vertical scales are much, much smaller than the horizontal scales. And for a long time, it's been known that stratified turbulence can be a source of layering. And it dates back to some nice work by Phillips in 1972, followed by some demonstration proof of concept by Poismontier and Bamforth et al. And then a beautiful experiment by Holford and Linden. And I'm going to tell you what's in these papers. So the Phillips mechanism goes as follows. So you consider the buoyancy equation, and buoyancy is just a proxy for the density perturbation away from the mean. And so it just follows a regular advection diffusion equation. If you average that equation horizontally, you get the standard, can you see my pointer here? Yeah. You get the standard average equation where you recognize here the turbulent buoyancy flux as well as the diffuse buoyancy flux. And then you put everything on the right-hand side, and you find that the evolution of B bar, this horizontally average buoyancy, is just d by dz of the absolute value of the buoyancy flux, FB, curly FB. The buoyancy flux in stratified turbulence is always negative, so the absolute value is just minus the buoyancy flux. And then the key here is if you assume that this positive part of the buoyancy flux is primarily a function of stratification only, so curly F is a function just of dB bar dz, you can take the derivative, use, it's called the chain rule, I believe, and you get, sorry, I haven't taught calculus in a while, and then you get F prime of dB bar dz times d2 b bar dz2. And that immediately shows you that if this F prime is negative, then you generally have what we would call anti-diffusion, where the coefficient in front of that second derivative is negative, right? So this is anti-diffusion in a really traditional sense. So that was the insight here. And if you have anti-diffusion, you expect this spontaneous layer formation. So the proof of concept for this idea was provided by Poismontier and Bamforth et al. A little bit later. So the idea is if you start with just this picture in mind that maybe the buoyancy flux does decrease with the buoyancy gradients for some parameters. So somewhere in parameter space, there's a region where this FB is a decreasing function of dB/dz. Then possibly you can get layer formation. So what they did is they literally assumed a flux law that had that property with different levels of complexity and put that in a simple 1D numerical simulation and obtained indeed the formation of layers in the density field. So this is just different times. This is the density profile. This is the paper by Poismontier. Showing the emergence of these layers. And then the nail in the coffin was probably these experiments by Holford and Linden in '99, Here is not their original experiment, but Claudia, Chini, Jim McElwain, and myself at Hui trying to reproduce them. Can I? How is? Why is this not starting? There we go. Okay, so you have a tank of water that is stratified with salt, and then you pass back and forth some rods at some particular well-defined speed, and you let it go for many, many hours, and after many hours, what Caulfield and Linden saw was the emergence of layers in the density profile. So they started with a constant buoyancy gradient, so a linear stratification, and over the course of 2, 4, 8, many, many hours, they saw the formation of layers. And so this really seems to match with this idea of the Phillips mechanism. And
some layers disappear with time.
Yeah, because it is mixing eventually. It's a constant amount of salt, so eventually the stratification disappears over time. But the talk could be ending here, and it did in '99, I'm sure. But is it really that simple? And that's the question I want to answer today. So here are some problematic issues. The first thing, and that's something we've realized by trying to redo these experiments, is they're fiddly. We haven't yet been able to, sorry, Claudia and Jim, and I'm just the watcher in the background, not able to reproduce these experiments yet, even at exactly the same parameters. There's something going on here. Secondly, if it was really that simple, you would expect layering in the ocean to be quite ubiquitous. And in some level it is. We do see layering in the ocean, but most of the layering that's observed we know is associated with double diffusive phenomena rather than just this pure Phillips mechanism. And then finally, this all assumes you know what the buoyancy flux is as a function of the buoyancy gradient, but it would be much nicer to be able to predict it from first principles rather than having to observe it in experiments. And then I just want to put a plug in as well for my real work, which is in astrophysical fluid dynamics. Most of the experimental work so far has been done for salt-stratified fluids, but what about other Prandtl numbers? So salt-stratified fluids are a very large Prandtl number. What about heat-stratified fluids? What about fluids that are stratified by a helium gradient, for example? So the Prandtl number can range massively. And so the question is, can we redo all of this and figure out maybe where the stars are layered or maybe where the planets are layered? And I unfortunately won't have time to talk about the second part, but just so that it's in your mind that there's a lot of work to be done in that respect as well. So what I want to talk about today is this toy model to try and study the question. So basically, we're going to assume a stably stratified fluid with a stable buoyancy gradient shown here. And we're going to apply a sinusoidal flow, a Kolmogorov flow, which is invariant in the vertical direction and then varies laterally like that. And it's going to be pushing the fluid in the x direction. So streamwise is x. And these are the governing equations. And now I'm splitting the buoyancy field into the background buoyancy gradient, which is n squared in these in here. So the buoyancy frequency squared, as well as the fluctuation b tilde. So this is the equation for the fluctuations to the buoyancy field. And we're going to use this triply periodic system for the velocity field, pressure, and buoyancy fluctuations. And when you non-dimensionalize these equations with some reasonable units, the unit length is just the horizontal shear scale, the unit velocity is the anticipated horizontal flow velocity, and then buoyancy is ln squared, L being the horizontal shear scale, and then the pressure. You end up with the same equations, non-dimensionalized, and you see the usual suspects, the Reynolds number, the Peclet number, and the Froude number. Reynolds is a measure of the inverse viscosity, Peclet is a measure of the inverse buoyancy diffusivity, and Froude number is the inverse stratification. So what this looks like when you spin it up from scratch, what I'm showing you is a view from the top. So going back to this, I'm showing you a view from the top here. And sorry, I need to remove the laser pointer. Why is it not? Sorry, somehow there we go. So the shear gets amplified by this constant force, and then it goes unstable first to 2D motions, and then very rapidly becomes unstable to 3D motions. You can see there's a lot of very small scales in the system. So this is still the transient phase. After a little while, the system settles down, and the force, the applied force takes over again and is going to drive these jets. So you can start seeing them now. And these jets are pretty dynamic. They're meandering around as a result of these large-scale instabilities as well as the small-scale turbulence that it drives. So you can just let it go for a long time.
The only driving is sinus y.
Just in the y direction. Sorry, in the x direction, but with a sine y. So the point is, it's very dynamic. And if you look at the simulations now for the whole box and fix the Reynolds number and vary the stratification, this is essentially what you see. This is pictures, again, of the streamwise velocity field. You can see that at moderate stratification, you have these meandering jets here, and they have a particularly well-defined vertical scale, and that vertical scale decreases with increasing stratification. So this is a more strongly stratified fluid. And so what happens is you have this velocity layering, and the way to interpret it is that each layer of the fluid is meandering at its own, in its own way. And then between different layers, the meanders are decoupled, so they're not in phase, and they generate quite a lot of vertical shear. And it's, at least in our interpretation, it's that vertical shear that causes a lot of this very small scale turbulence. So the point is, this system naturally gives rise to velocity layering simply from the decoupling of that horizontal instability in the vertical direction. And then the vertical flow that we are observing is what is going to drive this buoyancy flux. So the question I want to ask is really, what can we predict this buoyancy flux? It's a really hard problem for DNS, especially when you have in mind applications to oceanography, atmospheric sciences, or planetary sciences, because the Reynolds number and the Pascale number are typically asymptotically very large. And the Freud number, by contrast, which is a measure of the stratification, is asymptotically small. And so DNS is fine. We can do them for moderate Reynolds, Pascale, and Freud number, but if we really want to have some predictive power for astrophysical and geophysical fluid dynamics, we're going to need to do better. And so what we're going to use here is asymptotic analysis, which is validated by DNS in a regime where both of them overlap. So I'm going to start with the simplest case to explain on how this asymptotic analysis might work. And this is not our work. This is work by others. The point is, at the basic level, if you assume that you have these very large horizontal scales that might be decoupled in the vertical, you can also assume that the vertical scales are simply, or the vertical fluid motions are simply driven by the horizontal divergence, or by the divergence of this horizontal flow. And you end up with large scale vertical flow as well. They're small scale in the vertical, but large in the horizontal. So I'm kind of, the picture speaks 1,000 words, and my words are jet lagged. You get the idea, right? So we have one large horizontal scale, one small vertical scale. And so this is beautiful because you can do asymptotic analysis on that very easily. And so that was done by Bion and Chomaz and Brettauer et al. In 2007. The idea is to simply say that the vertical scale is much smaller than the horizontal scales. And so you create a new vertical scale zeta that is just z over alpha, where alpha is very small and presumably related to the stratification. And the goal of the analysis is just to figure out that relationship between alpha, the aspect ratio, and the stratification. So the next step is simply to take the governing equations with this rescaling of the vertical and also split the velocity field between the horizontal velocity field and the vertical velocity field. So just as an example, this is what dvu equals 0 looks like. We have the horizontal divergence of UH, the horizontal velocity field, plus 1 over alpha dw by d zeta, which comes from the regular dw dz. The key here is that the horizontal flow is going to be order 1 by assumption. This is what we non-dimensionalize it to be. And we're going to assume that the stratification is large, so this fluid number and alpha are both very small. So the implications of that are then it's kind of a little domino problem. So you start with mass conservation, and you look at it, and you realize, well, that's not going to work unless the vertical velocity field itself is small. So immediately from there, you get that the vertical velocity has to be of order alpha. You then look at the horizontal momentum equation, and I've highlighted things that are small or big. On the left-hand side here, everything is of order 1, because W over alpha is now of order 1. And then you have these terms there. That tells you that the pressure has to be of order 1. And then you can look at the viscous term here and notice that the correct Reynolds number for the system is no longer the original Reynolds number, but it's this rescaled Reynolds number, alpha squared Reynolds. And that's a very well-known quantity in stratified turbulence that is called the buoyancy Reynolds number. But because alpha is small, you can see that this buoyancy Reynolds number can be quite small, even if the original Reynolds number is big. And so in order to have any chance of being in a turbulent regime, we actually need this buoyancy Reynolds number to be at least of order 1 or bigger, because otherwise we're truly viscously dominated. So turbulence requires this RAB not to be too small. So in all I'm going to say, when I take the limit of very small stratification, I'm going to equally take the limit of very large Reynolds number so that the buoyancy Reynolds number at least remains of order 1 or bigger. Now, so we've learned that the vertical velocity is of order alpha. So now the buoyancy equation, that's what it looks like. Again, everything that's of order 1 is in black. Well, the thing here is of order B, because I haven't said yet what the buoyancy field size is, but that's all of order B, everything is of order 1. W is of order alpha, we just said that. Over here, this is of order 1 over alpha squared Peclet times B. And note that alpha squared Peclet, we're going to define by analogy with the Reynolds number as a buoyancy Peclet number. And it's just the Prandtl number times the buoyancy Reynolds number. And if the Prandtl number is of order 1 or bigger, then because the buoyancy Reynolds number is of order 1 or bigger, naturally the buoyancy Peclet number is of order 1 or bigger. And as a result, the diffusion terms there are not very important. And so the dominant balance, if we want stratification to matter, and stratification is contained in this term, that naturally tells us that the buoyancy field also has to be small, of order alpha. And then you go back to the last equation we haven't looked at yet, which is the vertical momentum equation, with vertical velocity of order alpha and b is of order alpha, because we just learned that. This is the vertical component of the momentum equation. Over here, everything is of order alpha. But this term, pressure gradient over alpha, is really large because it's of order 1 over alpha. This one is small because we just said the buoyancy Reynolds number is at least of order 1. And as a result, the only thing that can compensate that vertical pressure gradient is the buoyancy term. And essentially, you require a balance between these two things. That's called hydrostatics. And if 1 over alpha has to be alpha over fluid squared, you immediately get that alpha has to be fluid. And this is a well-known result that the vertical length scale in stratified turbulence under this model is simply alpha is fluid, or the aspect ratio is fluid. And so the vertical length scale is alpha times L. And if you just do the math, it's U over N. Right? So the horizontal velocity divided by N, the buoyancy frequency. And, the vertical velocity field is fluid times U, because it's alpha U. So This has been one of the really great successes of these lab experiments, is to demonstrate this vertical scaling for the length scale works very well. So these are, again, these experiments by Caulfield and Linden. They measured the emergent layer scale as a function of U over N. So this is U over N on this axis over here. This is the layer depth, and you can see this beautiful linear relationship where this vertical layer depth is just 3 times U over N. Again, almost too good to be true, but it really works. In terms of the RMS velocity, the prediction was that the RMS vertical velocity should be going like Froude. These are now some simulations at Prandtl number 0.1. Incidentally, what I showed earlier doesn't really depend too much on the Prandtl number, it just depends on the Peclet number. So these are all high Peclet number simulation. Peclet is 100, Peclet is 60. So these are these simulations that I showed you earlier. We measured the RMS vertical velocity as a function of stratification. So stratification increases to the right. And so WRMS going like Froude is this gray line. So you can see that it seems to work pretty well as long as you're sufficiently strongly stratified. So this all looks really nice. The only problem is that at heart, this anisotropic rescaling, where we assume a single horizontal scale, doesn't really gel with what we see in the DNS, which is this. So these were these snapshots of simulations at different stratifications for the streamwise velocity field. And here it really does look, there's one large horizontal scale. But if I look at the vertical velocity field, this is what it looks like. And now you can't even see this large horizontal scale. It's kind of disappeared, and the vertical velocity field is primarily small scale, both in the vertical and in the horizontal. So that appears to contradict this model in which there's a single large horizontal scale. So maybe we need to do away with this. And that was the argument put forward by Greg Chini and colleagues not that long ago, and I believe he presented that work 2 years ago at the Newton as well. KITP, right. So the idea here that they argued is that really a multi-scale model is needed, where, yes, we do have the vertical scales that are much smaller than the large horizontal scales, but we also need small horizontal scales because we see them. And these small horizontal scales are generated by the vertical shear between these large horizontal eddies in the picture that is shown here. So we have these little blue eddies, which are the vertical velocity field. And as you can see in this picture, they're mostly isotropic. So on the small scale, there's isotropy, whereas on the large scale, it's very strongly anisotropic. So to model this using multi-scale analysis, the first step is exactly the same. So there's a rescaling of the vertical coordinate with alpha. Again, alpha is a small scale, is a small aspect ratio. So zeta is z over alpha as before. But now the assumption is that every single quantity, which is normally just a function of the horizontal coordinate, this rescale vertical coordinate and time, is going to be split into a Q bar, which is going to represent our slow horizontal scales, and a Q prime, which is going to represent our fast horizontal scales. So XS is going to be the horizontal variation of these large scale eddies, whereas XF is going to be the horizontal variation of the small scale eddies. In addition, so now our horizontal gradient is going to be 1 over alpha grad F, so on the fast scale, plus a grad S on the slow scales. And associated with this horizontal rescaling, you need a new fast time scale, which corresponds to the little spin-up time of these small scale eddies. And that fast time scale TF is also T over alpha. So you end up with d by dt is 1 over alpha d by dtf plus d by dts. And so sort of embedded in this is this assumption that you now see that both the fast horizontal scale and the vertical scale were rescaled by alpha. So you have isotropy on the small scales. And the fast time is simply the vertical shearing rate between these eddies. So the anticipation there is that the dynamics really correspond to the shear instabilities between these horizontal eddies. So I'll just start this analysis because it really would take a whole talk to give the math. But just to give you a flavor of what it looks like. So mass conservation now, when you plug in this ansatz, looks like this. So you have the divergence on the slow scales and the divergence of the fast scales. You horizontally average, you average over the small scales and the fast time scales, and you just get this. And again, so you get the bar quantities, right? And again, that tells us that W bar is of order alpha. And in fact, all the dynamics on the slow scale will essentially recover what we had for the single scale model that I showed you earlier. On the other hand, you now take this equation and you subtract it from the total. You're left with just this bit. And you can see now each of these two terms have a 1 over alpha in front. So we now need the horizontal fast scales and the vertical scales, the horizontal velocity and the vertical velocity to be of the same order. So, and that's really a statement of isotropy on these small scales. And then for the horizontal momentum equation, if you look at the horizontal momentum equation average on the fast time scale and the fast horizontal scales, you get something like this. And it looks very regular. And you have this additional term here, which is the standard Reynolds stress. And the Reynolds stress picks up a 1 over alpha. And so for it not to be much bigger than everything else, we require that this quantity here be of order alpha. And because W prime and U prime were of the same order, each of them individually has to be alpha to the half. Okay? And so that's immediately telling you that the vertical velocities are now alpha to the half rather than alpha. So they're bigger than the mean vertical velocity flow, the W bar. And the other thing it tells you is that now the relevant quantity is no longer the aspect ratio, but the aspect ratio to the half. So when you want to do an asymptotic expansion, that is your parameter that you need to use for the expansion. Now, up to this point, everything is completely agnostic about the size of the Prandtl number. So what I said is completely valid across parameter space. The Prandtl number comes in when you start invoking the buoyancy. And what I'm going to talk about here is what happens for Prandtl number of order 1 or bigger. The next steps is basically substitute the ansatz into every single equation and again look for dominant balance both in the mean equations and in the fluctuation equations. And the results for Prandtl number of order 1 or bigger are as follows, and you can find them in Chini et al. Or in this new paper by Kasturi Shah et al. And as before, and that's very reassuring, we find that alpha is of order Freud. So the vertical length scale is unchanged compared to what we had discovered in the single scale model. And that's very convenient because that had already been validated experimentally. An interesting consequence of that is that if you compute the Richardson number associated with the shear instability of this emergent vertical shear between the eddies, that Richardson number is of order 1. And so this is the statement of self-organized criticality where the flow is just right to be sort of marginally stable, marginally unstable to these vertical shear instability on these small scale between these horizontal eddies. So it's not very unstable, but it's just enough to maintain a healthy level of turbulence on the small scales. And then finally, the main result is are these scaling laws, right? So the mean flow, so these large horizontal scales, they behave exactly as in the single scale model. So we have W bar and B bar are of order Freud, just like before. What's interesting is the small scales have a different scaling law, and we find that both the horizontal velocity, the vertical velocity, and the pressure on the small scales are of order Freud to the half, and the buoyancy field is of order Freud to the 3/2. And this was already intuited by Riley and Lindborg in 2013, but this analysis really demonstrates that this emerges naturally from this asymptotic multiscale analysis. So these are the predictions from the analysis. Now let's check against the DNS data. So earlier I showed you this plot. So I just want to say the vertical length scale has already been validated, so I don't have to go back there. But let's see what it predicts for the vertical velocity. So this is again the RMS vertical velocity as a function of stratification, with stratification increasing to the right. These are the data points for different Reynolds numbers and Peckley numbers. And the red line was this prediction that the vertical velocity goes like Froude, which is valid in the single scale model. And then the blue line is what the multi-scale model predicts, so Froude to the half. So the conclusions are depending on how strongly you believe in asymptotic analysis or not. The single scale model definitely seems to be valid for the stronger stratification. The multi-scale model, there's 2 data points that fit. It's pretty unsatisfactory, but maybe you might believe it works. So we would really like a better proof than this, because this is not very convincing. And to really understand what's going on, it's useful to look not just at this metric, but instead to look at the real data. So I'm going to take these points, right? This one here and this one here, okay? And I'm going to look at what the vertical velocity field looks like. So this is the vertical velocity field for the more moderate stratification, and this is the vertical velocity field for the stronger stratification. So you can see what's happening here is that at moderate stratification, it does look like most of the domain is turbulent and has lots of small scales. But as the stratification increases, the turbulence is really limited spatially to these patches of turbulence. So there's a lot of intermittency, both in time and in space. And so it's pretty clear then when you go back to this analysis that the single scale model is probably more likely to be valid outside of the turbulent region. So say here, where there's not a lot of small horizontal scales, but on the other hand, the multi-scale model is much more likely to be valid right here, where you do have a lot of small horizontal scales. So the
patches in between jets in opposite direction.
That's right. Yeah.
Where shear is maximum.
So yeah, exactly. That's where the shear is maximum, right? And it really comes from this layering. So you have these meanders are kind of flowing past each other and creating vertical shear. So when we want to compare the model to the data, we have to be fair in our comparison in as much as we only expect the multi-scale model to be valid in the turbulent patches and the more single-scale model to be valid in these more laminar regions. So the question is, can we actually find a metric to isolate the turbulent patches from the non-turbulent patches? And you know, when you talk to people who do stratified turbulence, or turbulence in general, they will tell you, well, turbulence is regions of high entropy. So here is the entropy. I'm showing you the same or very similar simulation as before. And it's immediately clear that the entropy is not a good metric because the entropy picks up these very laminar regions right here. And if you actually compute the different components of the vorticity, and you look at them in the light of this asymptotic analysis, it turns out it's not surprising. For example, the y component of the vorticity is dux dz minus duz dx. And while this one is of order 1 over Froude, because this is just the aspect ratio alpha, this one is going to be Froude to the minus a half. And this one is bigger than this one. This is the bits that would come from the turbulent patches, you know, lots of small scales in the vertical velocity field. This is simply these large laminar regions that are flowing past each other. And therefore, the entropy is actually more sensitive to the laminar regions than to the turbulent regions. But once you realize that, you know, the answer is quite easy because we just pick up the vertical vorticity instead, because the vertical vorticity WZ is dy dx minus dux dy. And that one is of order 1 in laminar region, but order 3 to the minus a half in the turbulent regions. And if you plot it, now you can see that it only picks up the turbulent patches. Okay, so the message here is that vertical vorticity is a much better tracer of turbulent patches for these intermittent simulations than the entropy itself. And so we're going to construct 3 quantities. One, which is the regular RMS velocity. Another one, it's an RMS velocity strongly weighted by this vertical vorticity squared. And that one, as you can see, because this is only big in the turbulent patches, this is going to be an average over the turbulent patches. And this is now the inverse. We're creating another quantity, which is the vertical velocity weighted by the inverse vorticity. That's mouthful. And that one, this is extremely small in the turbulent patches and extremely big outside of the turbulent patches. So this is going to be a diagnostic of the non-turbulent regions. Hopefully you get the idea. So, and this is the result, right? So the green line is what I showed you earlier. That's the regular RMS velocity. And then the blue line is the RMS velocity weighted to the turbulent patches. And the red line is the RMS velocity weighted outside of the turbulent patches. And now it becomes much more convincing that the multi-scale model really works, because that is the prediction for the multi-scale model. That is the prediction for the single-scale model. And you can see that both outside of the turbulent patches and inside of the turbulent patches, the models work where they should work. So that gives us a much better confidence as to the validity of the multi-scale model in the turbulent patch and the validity of the single-scale model outside of the turbulent patches. So the summary is, if you have just one large horizontal scale, these are your scaling laws. If you have both a large horizontal scale and a small horizontal scale, these are your scaling laws. Okay? Now, let's go back to the question of the buoyancy flux and layering. So dimensionally, let's go back to dimensional quantities because it's easier to work that way. The buoyancy flux is just the minus the buoyancy flux is just the diffusive flux minus the turbulent flux. And from the scaling laws we found, this turbulent flux is W goes like Freud times U, B goes like Freud ln squared in the single scale model. And then in the multi-scale model, W goes like Freud to the half, and B goes like Freud to the 3/2.
Which is the same.
Well, that is something that was unexpected, but it turns out to be this is very convenient because I only have to just deal with this. So both cases, the turbulent flux scales like Freud squared times U ln squared. This, again, that's dimensional now. And if I put back what Freud square is, I get U squared over L squared N squared times this. The U squared U becomes a U cubed. The N squares cancel out, and that's very important. And then you get U cubed over L. Now, for those of you who do turbulence, you know exactly what that means. It means that the power injected into the system goes, some of it into this buoyancy flux, and some of it goes into viscous dissipation at the same rate. So this is this notion of constant mixing efficiency, or rather mixing efficiency that's independent of stratification. As a result, the buoyancy flux is going to look something like this as a function of buoyancy gradient. So this is the buoyancy gradient here. This is the gray region is very weakly stratified. This is the region where the multi-scale or the single-scale model ought to apply. And this is where buoyancy diffusion begins to matter. So when you're unstratified, essentially the buoyancy field is just a passive scalar. And the buoyancy diffusivity in that case is just a turbulent diffusivity, which I'm going to estimate is U times L times the buoyancy gradient. In this region, we just have U cubed over L. And then here, it's going to be dominated by just microscopic diffusion of buoyancy. So that's the prediction. And then the model itself looks like this. sorry, the DNS data shows something like this. So now I've rescaled it by u cubed over L here, and I've rescaled it by L squared over u here.
But the slope is everywhere non-negative.
Indeed, absolutely. Well, it is true here too, right?
Yeah.
So the model predicts there's no room for negative slope. The data confirms there's no negative slope, okay? And these are two different Peckley numbers, so you can see that at slightly larger Peckley number, the effect of buoyancy diffusion kicks in later, but this is sort of more or less flat, and so it seems to satisfy the model quite well. So the prediction is no layering. So what does the data say? I'm going to look at these two data points, and I'm going to plot the buoyancy gradient in the vertical. I'm going to show you some movies. So the vertical, this is a snapshot. Sorry, it's a picture of just the XZ plane. So it's not horizontally average or anything. It's just a slice through the domain. And the color is just the buoyancy gradient. So red means strongly stratified. It's an interface. Blue is not stratified. It's just a layer. And this is so here, this is what it looks like for the slightly more weakly stratified case, and this is what it looks like for the slightly more strongly stratified case. The point is, these interfaces, they appear, but they're very dynamic. They're not self-reinforcing in some sense. They just move around with the flow. So these velocity layers that I was showing earlier, they just advect these interfaces around. Sometimes they destroy them, sometimes they help reform them. But there isn't any density layers in the sense of the Holford and Linden experiment that appear here. And that's not inconsistent with, and Alexis might confirm, this is not inconsistent with oceanographic measurements, that they have these interfaces that come in and out, but they don't live for very long. And it is consistent with this notion here, that if we really believe that the gradient of the buoyancy flux is this effective diffusion coefficient, right now it's 0, right? It's flat here. And so the interfaces are, there's neither diffusion nor anti-diffusion. It's just flat, okay? So if anything, they might grow the layers might grow linearly in time, but it's definitely not an exponential instability. So the conclusions are, so with this combination of asymptotic analysis and DNS, we have some robust predictions for the scalings for the scale, the vertical velocity, and the buoyancy in these two different cases. This is the prediction for the buoyancy flux, and you can see there's no region where it's decreasing with the buoyancy gradient. That is for the constant forcing case, but it's quite robust in this case. The implication is that there's no density layering, and they're not found in the DNS, so that's consistent. Which begs the question of what the heck is going on in the Holford and Linden experiment? Something else, presumably another effect that's not taken into account, is there. And if you want to know about the low Prandtl number case, please ask me, because I didn't have time to talk about it.
Okay. We have a healthy amount of time for questions. Edgar.
That was wonderful. Thank you, Pascale.
Thank you, Edgar.
Can you say something about the white region with the very strong stratification?
It's just viscously dominated.
So that's the reason why your data does.
It just drops out. It almost drops out of the plot. The vertical velocity gets very strongly suppressed, and so does everything else. Yeah.
After you analyze the order of different terms, you know which to drop.
Mm-hmm.
The remaining seems to be possible to solvable analytically, for which if it would be good to compute a mean profiles, let's say, that would be a great challenge for theoretician to derive it.
So
just y dependence and z dependence of your mean velocity and mean flux, VP, this correlation. So at least these two quantities, I would love to see profiles. It would be a great challenge for me to compute it.
So Greg
Or for
Chini
us,
here.
statistician,
So one of the things I did not have time to talk about is the beauty of this asymptotic analysis is it leads to a self-consistent reduction of the entire set of equations to a quasi-linear system.
Yes.
In every parameter regime that we looked at, right? So this reduction to a quasi-linear system is very robust. It's a consequence of these two scales. But as a result, yes, absolutely, there's a lot you can do that's either analytical or semi-analytical. But I'll defer to Greg because he's the expert.
For force sinus y, it must be solvable analytically.
Steve?
Very nice talk, Pascal. In your multi-scale model, you have these turbulence patches of a certain size. Is that the size you're associating with the large length scale in the horizontal, or do you have few horizontal large length scales in any given turbulence patch? So do you have 3 length scales?
You know, I don't know the answer to that question. To me, they look like they're the size of the meanders, right? But I am not sure, because unfortunately, we're not able to do much bigger simulation to see how it scales with that. Yeah. Yeah. But this is very new stuff, so lots to look at. Yeah.
Are the gravity waves also part of the fast time scale, or it's just mostly isotropic like turbulence? Because
So that's
your
a
pictures, yeah, they were like wave fronts moving a bit.
So I looked a little bit by eye at the gravity wave field, and what's interesting, so these simulations take a really long time to spin up. And so as a result, often when I look at the very high resolution ones, I take a simulation of the particular stratification, and then I restart it with a higher stratification to avoid having to respin it up from scratch. When I do this, I see lots of gravity waves in the initial phases, and then they die out. So there's something where maybe it's the turbulence that kind of kills the gravity wave field, but once the system has settled down, I don't see very many gravity waves anymore either. So the interaction with the gravity wave field is something we haven't looked at, but my reading of the simulations is that very rapidly they disappear. So maybe we could chat about why.
Alex?
There were the 2 predictions for the multiscaling and the older multiscaling, and it seems that when you do not do the conditional averaging, you follow the lower bound, not the upper. So which the one that drops faster?
When you don't do
The f minus 1 instead of fruit number minus 1 instead of fruit to the square root, 1 over square root.
When you did not conditionally average.
Oh yeah, yeah.
Yeah, it seems to go to the lower, to agree more
Yeah,
with
that's
the lower
right.
bound.
That's because the full averaging is an average over both the turbulent patches and the non-turbulent patches.
Yes.
And so obviously, when you look at that, it's going to be dependent on the volume fraction of the
That's my
turbulent
question.
patches.
Do
Yeah.
you have an estimate of what is the volume fraction as?
I would love to find a way, and we had this chat with my collaborators, on how to extract that volume fraction without any artificial user input. So, because you could certainly say, I'm going to define this volume as where, say, the kinetic energy in the vertical velocity field drops below a certain value, but that value is my input. So I could do, I would love to find a way of doing this outside of user input. And if you have some ideas, I'd love that. But yes, the volume fraction by eye, you can see it decreases very rapidly. So that's why it goes to the fruit to the minus 1.
David?
Presumably in these experiments, they're quite subtle, aren't they? I mean, as to whether the forcing gives layering or whether it doesn't give layering. It's like in Neil's model. There are some things it does and some things it doesn't. So presumably your Colmogorov flow is not really what Holford and Linden are doing.
Maybe. I mean, in here, the assumption is that the forcing is purely horizontal. Maybe if there's a little bit of vertical forcing, you might get a different scaling law, because then you would have a large W that's kind of on the large scales as well. But I don't know. I mean, we had a chat with Paul and Stuart and Claudia and Jim about what's different, and we haven't nailed it yet.
Quick question?
So just comment. So once you start asymptotic expansion in multiple scale analysis is a kind of derivative expansion. So then turbulence itself as a whole is not at all isotropic. Okay, it's all the inhomogeneity and anisotropy enter from the higher order terms. So in this sense, the image of turbulence is not at, even in small scale, not at all isotropic. You can relax the assumption for the small scale turbulence is just isotropic.
It has to be a little bit isotropic. I mean, it can't be.
Yeah, of course, a little bit isotropic.
It doesn't have to be fully isotropic, but it has to be order isotropic.
Okay, we've got to move on.
Okay.